Now things will start going right. Good old physics will get us sorted out. All right, so let's, new homework assignment. Rodney, would you please hit the light? All right, so we've got homework set number 3. It will consist of Chapter 2, Problems 40 and 47, and Chapter 3, Problems 4, 7, and 12. And that will be due a week from today. These 47 is kind of a math problem. 4 is not, so these are not like super hefty problems for you. So we're going to go ahead and have that be due a week from today.
No math CAD code?
No math CAD coding. You'll just, this is just an opportunity for you to just relax. Still do the homework, but you know. All right, so it's going to be due, I think that makes it October 7th, yeah. And we've already done all the material for all of these problems, so you can go ahead and start at any time. All right, so let's move on. So last time we were talking about center of mass. We're sort of doing a pretty good job at getting through this momentum and angular momentum chapter, which is what chapter number 3 is. And so we just need to discuss angular momentum next. Okay. And in this case, we're going to get another conservation law, and there will be certain conditions under which angular momentum will be conserved, and we'll say in that case that the system is isolated angular momentum-wise. So we have lots of different ways for systems to be isolated. But before we do that and get to that conservation law, we're going to review just sort of the angular momentum formalism first. So a lot of this hopefully will look familiar to you. So we are going to define if there is, let's say, a particle located at some location R that is moving with some momentum P, all right? Where momentum is mass times velocity. So there's the particle there. And this is just the origin of my coordinate system. Okay, so in that case, we would say that this object has some angular momentum about the origin. And because it's a single particle's angular momentum, we're not going to use capital L, we're going to use lowercase l. And because lowercase l looks like a 1, we're going to make it cursive. Right? So lowercase l for this one particle is equal to its location crossed with its momentum. All right. And yeah, I can do some more with that. R cross MB, that's fine. I could even do a little bit more with that. Might be premature, but let's do it anyway. Let's say that this is R times M, where V is related to some sort of omega. Well, that would be if it was at a fixed radius. It might be premature. We'll save that for later. We'll relate that to circular motion just a little later. So we'll stick with this for right now. Let's put a box around it. These will be our defining statements for angular momentum. And angular momentum will be represented for a single particle by lowercase l. All right, now the thing is that this expression gives us the angular momentum for this particle that's located at r, that has a mass m, that's moving with some velocity v, but it only gives its value relative to the origin. If you were to calculate its angular momentum relative to some different location, you would get something else. So this expression gives us the value of L with respect to, W/RT is always going to stand for with respect to, the chosen origin. And only with respect to that origin. If you wanted to know its angular momentum with respect to some other location, you would have to choose your coordinates differently, your coordinate system. So at that point about which you want to know your angular momentum is your new origin. Okay, so let's say that we stick with the chosen origin and we're okay with it, and that we want to think about this variable here. Well, let's think about, we have that variable. Let's also think about that variable's time rate of change. Right? Okay, so I'm taking, in order to have the object's time rate of change, I'm taking the first derivative with respect to time of that object. I'm going to go ahead and make a substitution from my definition. Good enough. And now I need to apply my product rule, which I figured out works for the cross product in a previous chapter, in chapter 1. So I wind up with dr dt crossed with p plus r cross dp dt. Okay, so this is my expression. Now if I look at this first term here, I see that I get v cross p. Okay, and if I look at my second term here, I see, well, oh, in order to have a time rate of change of momentum, there must be a force. So that's one thing that's very good to know, is that in order for there to be a change of angular momentum, a force must be acting. And this is where that force comes in, is right here. I'm going to go ahead and make that substitution using Newton's second law in its original form, F equals dp dt, to note that dp dt must be equal to the force on the object. Okay, so this first term here, that is the cross product of v and p. Well, I noticed that there's p and here is v. They're in the same direction, so what's their cross product? 0. Very good. All right. And now I also have this second term here, which is a time rate of change of angular momentum. And like I said, in order to change angular momentum, one must apply a force. But it can't just be a force. It has to be a force at some distance, and also that has a perpendicular component to that distance, that vector that represents that location where the force is acting. So we're going to give that a special name, and we're going to call it the torque. Okay. And we are going to, in the past, we have represented torque with tau. We are not going to do that in this book, however. We're going to stick, in this course, we're going to stick with the convention of the author, which is to use the capital letter gamma for torque. Okay. So let's go ahead and talk a little bit about torque. I guess I should go ahead and write the defining statement. Okay, so we have our defining statement now for torque. And the interesting thing is that we also have this statement here that is really sort of a Newton's second law for angular momentum, which is that if I have a torque, now here I maybe considered that there was just one force acting. There could have been more than one. But so what I get as a result of sort of looking at this and thinking about it is I see that the net torque on an object is going to be equal to that object's time rate of change of angular momentum. And I could go capital L there, but so this is only for our point particle. This is actually going to hold more generally for extended systems and multi-particle systems, so I'm just going to go ahead and write it with a capital L. So capital L is going to be when I have a sum of lowercase l's, just like P total was a capital P for momentum when I had multiple momenta or momenta of an extended object, which is indeed just a bunch of point particles. All right, so I get this expression here, which I can say, oh, that's what came out of this derivation, but it deserves a name of its own. And it is Newton's second law for angular momentum. And, no, I'm sorry, for rotation. Sorry, not for angular momentum, for rotation. Okay. And so, and I see that it is analogous to Newton's second law for translation, which is that the net force is equal to the time rate of change of momentum of a particle or system of particles. And usually we think about Newton's second law as being simplified to F equals ma. That's fine, but this, we should remember, is the original statement. And so we definitely see that there's an analogy here. And you can imagine that this expression here is also going to give us an equation of motion for the rotation of an object. All right, but that's just a preview. We'll get there later. All right, so what we want to start talking about before we talk about that idea of finding the rotational motion of an object, firstly, we'd like to talk about the topic of this chapter, which is angular momentum and its conservation. All right, so there are some cases where we can sort of either maybe choose a special origin such that the torque is zero. Like, let's say there's only one force acting. If you were to consider the point along the line of that force, then torque due to that force would be zero. We'll talk about things like that later. But for right now, I guess I should probably write something up. For some problems, we can choose an origin such that the net torque on a system is zero. Sometimes this happens because there are no forces acting, but sometimes it happens because of a choice of coordinate system. Such that the origin is chosen in a way that yields the torque to be zero. An example of that would be, like, let's say that you wanted to talk about the solar system. If you wanted to look at the solar system from our point of view, there's lots of things going on, and obviously planets are being torqued and being accelerated, and all these things are happening to it. But if you wanted to look at it from the point of view of the sun, if you wanted the sun to be your origin, then the net torque is zero. Do you know what I'm saying there? So that would be, sometimes you just want to make that choice of coordinate system. And in that case, relative to that coordinate system, you'll have the net torque is zero, and therefore relative, again, just to that coordinate system and that origin, the time rate of change of the angular momentum relative to that origin will also be zero. And that will lead to a conservation. All right, so in that case, if the torque is zero, then what we have is dl dt is equal to zero. You can multiply both sides by dt and integrate, which will give you L final minus L initial equals 0. Or L final equals L initial. That's another fine way to write the statement that, is going to be our statement of conservation of angular momentum. Okay. So let's just, as an aside, remind ourselves of the conservation of momentum itself, translational momentum. All right. So as an aside, remember Newton's second for translation in its original form. Net force on an object is equal to the time rate of change of its momentum. And we multiply both sides by dt. And I'm going to go ahead and write this as net instead of with the summation sign. So I've got dp is equal to f net dt. I'm going to integrate both from initial to final. And I get p final minus p initial is equal to the integral from t initial to t final of the net force dt. Okay. And so what is sort of conventional is to take this right-hand side of the equation and say that seems like something that's important enough. Maybe it warrants a name, although maybe it doesn't. But it does have a name. We call this the impulse. And whenever the impulse is 0, we say that the system is isolated momentum-wise. I'll go ahead and note that impulse, sometimes I, sometimes it's J. All right. And in that case, then this expression yields that P final equals P initial. And we have the conservation of momentum. Okay. And there are multiple ways in which the impulse can be 0. Yes, the net force could be 0. That would be fine. But it could also be that something happens as a collision or an explosion or some other thing that takes infinitesimal amount of time. Therefore, T final and T initial are equal to each other because we can approximate it as taking 0 time. And in that case, this right-hand side also would be equal to 0. So, okay. So that's the thing that I want you to have in mind. Okay. As we move on to what we want to discuss now. Okay, so now we're doing the exact same thing, basically. I'm going to state that we just found our Newton's second law for rotation on the previous page, and I'm going to rewrite it again here. Okay, and again, I'm going to multiply both sides by dt. I'm going to flip it so that it looks the same as it did up here. So I get, and I could be doing lowercase l's too. That would be fine. All right, so I would get dl is equal to gamma net dt. I'm going to integrate both from their initial to the final value of their integrating variable, and I get L final minus L initial is equal to the integral from initial to final gamma net dt. And then again, I have this thing on the right-hand side of this equal sign. Does it warrant its own name? In this case, no, no name. But it is sort of a special quantity because if no name is equal to 0, then the system is isolated angular momentum-wise. Momentum-wise. Okay? And when that is the case, that the system is isolated angular momentum-wise, then angular momentum will be conserved. So that means that for all later times, L final will be equal to whatever it was at the initial time, L naught. Okay. Another way of saying that is that L as a function of time will be a constant. All right. Okay. Now, I take a moment to look at these. I'll remember this equation actually has its own name. Does anybody remember the name of this equation? This guy here? Got to go way back. Does anybody remember it at all? Yeah, that's what it is. It's the impulse momentum theorem. But really, the only reason that we gave that a name was because when you learned that name, you, in theory, didn't know how to do the step of math that is prior to it. Do you see that? When we gave that a name because we needed you to have a name for that, because we couldn't just say it's Newton's second law, and then you just do Newton's second law, right? It's not an algebraic restatement of it, but it's a rearrangement of it. It's just a calculus rearrangement of it. So now we don't have to call that impulse momentum theorem anymore. It is really just Newton's second law. Okay, all right. So we've graduated to that, I guess. And so again, this equation here also doesn't need a name. And that's actually no name. So okay. Anyway, none of this stuff needs names because it is really just a restatement. Just like this was a restatement of Newton's second, these are all just restatements of Newton's second for rotation. Okay. Alrighty. So are there any questions about that? The conditions under which angular momentum is isolated or anything? Or is conserved, sorry. Okay, so let's do an important example of the conservation of angular momentum. The central force. Okay. So in this case, let's say that I have a star and I have a planet. Okay. All right. And so really the star is much bigger than the planet. All right. So if I choose to make the location of the star the origin, so I'll just note that I have a star, and that star is going to be located at what I'm considering to be the origin. All right. And then over here I have this planet. All right. Now, let's say that I want to think about the torque from the star on the planet. Well, the planet is located at the location R relative to the origin, and the force that is being applied to that planet is a gravitational attraction, a pure attraction. So there's the force. It is anti-parallel to R. So in this case, the torque due to this force from the star on the planet, so just have this. This is my only system. This is the only other force acting on it. The torque is R cross F. And so in this case, that would be R times F times the sine of 180 degrees, also known as 0. Okay? And I should have noted there would be a direction here, but that would be the right-hand rule. Okay. But in this case, it's undefined anyway, so 0. Okay, and so because if I choose this origin, the torque is 0, then relative to this origin, the angular momentum of that planet is constant. And I should note that this is only true relative to the chosen origin. Because again, if I were going to be looking from somewhere, say down here, then I would say, you know what, that guy has an angular momentum of R cross P that is sometimes going to be, you know, R, maybe initially he's moving this away, around, you know. So if I have an origin down here, I have R cross P. It's associated with the out of the phase direction. And later on, after the planet's gone around, it's down here, R cross P would be down. Clearly, about this origin, angular momentum is not constant. Right? So you have to choose your system wisely. You choose your origin wisely. Okay. Okay, so the other thing that's interesting about this result is that L is equal to R cross P. And that is equal to a constant. What that means is that R and P must remain in a single plane. That's supposed to be an and, like an ampersand. I'll rewrite that. And that plane must also contain the sun. Sun. Sorry. Okay. So my question to you is, I hope that you see that that is a cause and effect, although you probably don't. Let's have you discuss that with your neighbor, why we have this single plane that also contains the sun. We call that an ecliptic, right? It's just the plane for a planet that's going around the sun, that little plane that they stay in. Why must R and P remain in a single plane from the previous statement? So have a conversation about that. Everybody talk to somebody, please. If they didn't, that's a great place to start. Okay, good. Did you have a chance to talk to your attorney?
Yeah. Well, I listened. It was kind of the same conclusion.
So it's cool if I call on you?
Yeah, that's fine.
All right. All right, I'm going to go get them.
No, yeah, I know. I don't know what she was asking.
So
Because
let's see. Oh, yeah. Okay, go for it.
So if they're not in the same plane and they won't equal 0, so then it would be
Yeah, that's true.
pretty much.
But why? Can you give me the why statement? Why is it that if they left the plane, L couldn't be, dl/dt would not have been 0?
Then the cross product, or the cross product wouldn't work. Like it wouldn't be able to equal out to 0.
Let's see. Plane. I think gamma would still be 0 if they left the plane, though, right? Gamma would still be 0 if they left the plane.
Oh, you're right.
Yeah. But that's so. Let's. Was that your argument too, or can you add something to it? Okay, then you guys need to retalk.
Okay, let's retalk.
The cross product is still be 0.
Why? Why does this statement follow from that statement, or how?
Because it's not in the same plane, it wouldn't be the concept. Like what one.
You're looking at from a different range angles, which it would actually look like. Well, if you looked at star falling around that, moving through space.
So you're reversing your frame of reference.
Well, yeah.
Like you're just looking at the plane instead of the star.
Yeah, if you're looking at them like you're the frame of reference.
And then the plane would be the origin instead of the star.
Yeah, the angular momentum would be constantly changing, but when you set the star as the reference, the angular momentum would still always be instead of right.
Move gradually.
But if you're looking at the plane,
If you think about just how planets everything in the universe is moving right now,
You're outside perspective looking at the singular planet being done at a certain. It wouldn't. The star would not. Because this isn't so revolving.
Normally,
the stars always change the sun.
like,
but if you're looking at
At a long period of time.
No, it's
A significant long period of time.
So
How long does it take for the sun to orbit?
So
into a galaxy?
if they were not in the same.
I know,
But if you
you're
look at the
things
planets,
like,
you
you
look
certainly
at
don't want to stick
but
with
if you
that
look at the
previous
planets, and the
sentence.
planets, you want
Because
your frame of reference
no,
to
that's
look
not
at the star,
true.
but you're
So,
actually.
like, let's
Wait,
say that
Gravitational pull from
you're
the
here,
influencing the sun significantly. It's gonna be a lot
and
less than
you're acting with
Earth
forces,
is the planet and
and
sun.
as a reflection, as what you're displacing
well,
in
alright.
No, I meant the star.
Let's say that's the center
maybe a
of the
force,
universe.
you got an
Long plane.
So you only take the parallel component of the force to the
That's your
displacement
star.
Yeah.
for a work.
That star is
You
moving.
don't take
Are you
that
the same?
perpendicular, so that cross
That your
product
reference
isn't generally
Kind of
gonna
in the center of
come
the
into
universe.
work.
Yeah.
Well, that's
I don't know
very
exactly.
condescending of me.
Orientation,
You just do the arrows.
how we fade it, but I don't talk
Okay.
about that more.
But yeah.
So let's just pick this up.
That's
All right,
the orbit.
so did anybody convince themselves of the ecliptic? That there must be a single ecliptic? Did you get there? I'm asking you, Ryan, did you get there? No, that's all right. Okay, then I'm just gonna, why don't I go ahead and do that?
You can see that.
Okay, I think I will. Just because you said so. All right, so what we have is a situation where what I have told you is that I've got the sun at the origin here, and I've got this planet that goes around. Oh, that's supposed to. Okay, well, whatever. That's supposed to look like it's stuck, like it's lying in the XY plane. Okay, that's supposed to lie in the XY plane. It doesn't, but okay. Anyway, so then if you think about what if sometime later, so we're going to think about the opposite. What if sometime later the particle was, the planet was up here? Right? So somehow maybe the planet went from being here to being up there. You see that? What would be, and before it's lying in the plane, so its angular momentum, the r cross f, the direction associated with angular momentum would be this away. Right? And that's going to be a conserved quantity. Is it possible for this particle, let's imagine that it traveled some path that was kind of like, took it off of its ecliptic and took it up like that. What would be the direction of the angular momentum while it was doing that? Would it, yeah, it would be boink. It would be like, it would not be here, it would be boink, like that. All right. So that would be completely inconsistent with having a constant angular momentum. Now, it could, you could have something like that, and yes, you could still use this origin. Now, I'm not saying that this planet could do that. We're talking about, you could still have a trajectory like that, but this would still be the origin, and what would happen with the planet on that trajectory is that it would have a different ecliptic, like this. Does that look tiltier? So that as L is going that way or something. Anyway, you get it. So as long as L is conserved, R and P must be contained into a single ecliptic, because you'd have to change the direction of L to move out of the ecliptic. Okay. All right. I was hoping you guys would come up with a better example than me, because that's why I actually had you guys discuss it. Whenever I don't have a good explanation, I always have you guys explain it, and then you do 10 times better than me. So but if this suffices, good. All right. Okay, so next thing we need to talk about is not Newton's, Kepler's second law. I know. Not everything belongs to Newton, regardless of what he thinks. All right, and those of you who are in my 240, 250 class probably know the story of Kepler's laws. Does anybody remember the players in that story? Tycho Brahe. Very good. So we had Brahe. What did he do?
Who? Brahe?
Tycho Brahe.
He just had money and bought expensive equipment.
Yes, he
and
did.
Hired Kepler to use it, and he kept all the data.
Yes, he kept data. So he spent his whole life taking data on planetary locations with this really expensive sextant that he had that could, provide many, many significant figures on those angles, those recorded angles. And from those angles, Kepler, who is asked by Brahe on his deathbed to do something, because Brahe himself was not a mathematician or anything, he just was an enthusiast about this data. He asked Kepler to figure out what he could find from the data. And so what Kepler found were 3 laws. And we have planets move in ellipses with the sun at one focus. Not circles, as had been previously posited. He also found that the planets' locations, if you think of that as a point, they sweep out, or think that line that connects the location to the sun, it sweeps out an area, and that planets sweep out equal areas in equal times. For a single planet, a planet sweeps out equal areas in equal times. And this is interesting because, again, if we've got, here's the sun, and now we've got these planets that are traveling these elliptical orbits, you can imagine that they're moving faster when they're closer. They're sort of winging around the corner, so that in some amount of time, maybe they sweep out that area there, and in the same amount of time, they sweep out that area there. And these 2 areas, if those are equal times, would be equal. All right. And then the last is that the period of a planet squared is proportional to the length of its semi-major axis cubed. Okay. And we're going to derive all of them from Newton's laws, but we're going to talk first about, no, really? Oh. But we'll pick up next time on that one. All right. I will see you Monday. I'm sorry about being late today.
All right, we understand.
I was talking to my chairman. It's my first chance to tell him. Terrible.